Hi guys, so I'll be showing you some of the Go. I'm currently learning Go and Golang. So I'll be demonstrating some of the things from Golang itself. If you can see my screen here, I have written a Golang. I've imported a format package, and I'm trying to print hello world. Here I've added a breakpoint, but I'll not get into that right now. First of all, I need to run it. So just run it. So it prints hello world, as you can see here. And then if you can debug it, as I have added a breakpoint, it will break here, and you can see see any of the variables that are there. You can check any kind of variables that can be seen. So currently there are no variables, so it does not show anything, or we do not need to add anything. So let's continue by pressing so the debugger. Okay. Oh, sorry, we can resume the debugger, or we can get a step over one step. Okay. So if we step over this function, then it goes to the return value, and it has already printed hello world here after this line, as you can see. This is execution point now. We can step over and the program runs the defer logic. I'll get into that later. So here you can see some of the variables that are there defined here. Let's not get into that right now. We can simply continue the program and end the program. So let's begin by here, as you can see, the alerts are actually alerts for keyboard shortcuts to these step into resume, then debugging, or other related shortcuts to various buttons in this IDE. So let's for beginning. So let's go for this. There are various types of values that can be assigned to variables. So as you know, Go is a statically typed language. So there are various values such as int. So int is actually an integer, and if we write println printf. If we write a formatted printf with value and then the type as here with printing the values. This is actually I put int here, which is perfectly valid identifier. Just that it's in conflict with the data type of the built-in data type. So it won't give any errors. It will run. If we try to run this program, then it will definitely run, and it provides the perfect value with the value of 5 and the type as int. But let's rename this with pressing the shift plus F6 and then rename into num. And then rerun. And as you can see, it rerun and gave it the proper value. So this is a type of int, and there is, if you want to define it as a integer with 8 bits. So 8 bits, that is 0000000. So these are 8 bits. If we want, if this is 5, that means this should be 0101. That actually is within the 8 bits value. So this runs perfectly if we run it, and it properly gives that it is a 8-bit integer type. And if we go for some more values, like let's say the highest value that can be put here is 1111 and 111. So this is the highest 8-bit value that we can put here, but that is not the case. The highest value that we can put here is 255 positive value, because this is a okay. 255 also cannot represent it. In 8 bits, I can represent a maximum of how much? 127. Not even 8. 128 is 127. That's a positive 127. It goes from minus 128 to even 129 is not important. Minus 128. If you run this, from minus 128 to positive 127, as you can see from below here. And if we want some more values, like if we want to store 255, we need to use an unsigned int 8 bits. Unsigned in the sense that it will use the whole 8 bits rather than 7 bits. Here, if we do not, for unsigned, for signed, it will be using only 7 bits, and for unsigned it will use 8 bits to represent the value that you specify. So that's the reason we are able to write 255 as the value. As you can see, I run, and 255 is the value with the int 8, unsigned int 8. If we try to write 256, it won't work, and if we try for any negative numbers, even it won't work. It's because it starts from 0 till 255, which is stored in an unsigned 8-bit. If we go for some more values like 250, if you want to type some more values like 256, you can write uint 16, which ranges for some quite a big number, and you can write, I think, 65535 for 25. Yeah, even 536 is not allowed. So for a range from 0 to 65535, if we calculate divided by, so if we run it, so 65535 is the maximum unsigned integer value that you can store in 16 bits. So if we go for signed 16 bits, signed 16, then you can store up to a maximum of 32767, starting from minus 32768. So yeah, if we run it, then yeah, minus 32768 is an int, signed int 16. So and if we go for positive value, then it's up to 32767 int 16. Let's say if you want to store a bigger number from this 32768, then you need to take a 32-bit integer value. So this will store even more range, starting from negative range to positive range. And if you are not looking for any negative ranges on only bigger positive range, this will int 32. If you use int 32, then it will assign the most significant bit as the sign bit, and the rest 31 bits will be used for defining the number, representing the number. And if you use unsigned int 32, then it will use all 32 bits to represent the number. So you can store a much larger number, but it will only be a positive number. And there is int 32, and I guess there is no 64. Yeah, there is 64 as well. So U6364 can store even a bigger number, which will use 64 bits of the number. And if you want to go for the negative connotations, negative side of it, it's a very large. It can store a much larger number. So if you go from a large negative number to a large positive number, can be stored in int 64, and this one overflows in 64, right? Okay, if we use unsigned, and then I guess this might not overflow. Okay, still this overflows. Let's see this. Okay, this one still overflows. This works. So int 64 is the number type that can be stored in unsigned int 64 bits. Can we go more than that? Is there 128? I guess for this, I don't think there's 128. Okay. So if we go for the other values, like if we want to represent floating point values like 1.2133, so this will give us a floating point float 32 into a number, in which so if you look into the standard for the floats or the constants, you can see that it uses for floating point literal, it uses this kind of IEEE 754 -2008 specification to represent a floating point number, in which you can even represent a floating point number using various different formats, notations, that is decimal notation, binary, using different bases like binary notation, decimal notation, octal notation, and hexadecimal notation. If you want to try for a binary notation, so some of the things that I wanted to tell you is that if we write as an int, you cannot start a number with 0, 1 for a decimal. If you want to represent a decimal number, because this if you start a number, any number with 0, then it automatically takes it as represented in octal notation, and accordingly it gives a value of 8 if we represent to the decimal, converted to the decimal counterpart. So you cannot start a decimal number from 0. So you need to start with starting from 1 to other values. So this will give the actual output. If you want to write a binary notation, you can write capital or small b, and write the number 10 is in binary, which represents 2 in decimal. And if you want to go for octal hexadecimal, then this will give you hexadecimal a value. A is represents is converted to decimal is 10, as you can see here. So this is various ways you can represent integers, and similarly you can write float 32 with various notations, that is the scientific notation and natural and normal notation. Using normal notation, you can use hexadecimal values like this. If you go from by the specification, as you can see, decimal digits. If you write hexadecimal float literal, a float literal can be a decimal float literal or a hexadecimal float literal. If you go by the definition, hexadecimal float literal is written as 0x smaller than hex mantissa. Hex mantissa can be hex digits. So this dot a can represent, this should represent a hexadecimal number. Okay, and then the exponential part should be present as well. So what this does is it multiplies 2 to the power 1 or 2. If we go by the this will give us 4. I guess this should give us 4. Yeah. So as you can see, this raises power 2. 2 square, so 1.0 into this actually is 1.0 multiplied by 2 to the power 2. So this is representing that. If you write as 3, then that means it represents which is 8 point. If we go by the rotation of here, if you want to represent only 2 with 2 number decimal places. So, okay, so it represents 8, but I'm not sure why there should be, if there is a decimal place, if there are decimal places, then if you give 0.2, then it will represent with 2 decimal places. So here, this is how you can write the floating point numbers in hexadecimal and scientific notation. So as you can see here, the exponential part must be written as p and plus or minus decimal digits. So decimal digits is represented as in like this. You can even represent this 3 as 0b11. So that is also that should be fine actually. Decimal digits. Okay, this should be decimal digits, not any binary digits. So you need to write as decimal digits only, not binary digits. And you can, if you are representing a very large number, you can write it as 1.1 1,000 or if you want to represent bigger, a binary number, so you write it like this. So this underscore can be used for separating digits of a number, and while evaluating it will be ignored and it won't be calculated as such. So that's float 32, and to represent bigger floating point numbers, that is float 64, and let's see if 128 is there. No, 128 is not there. So we have float 32 and float 64. And if we are going for a complex, or that we can also represent a complex number. How to represent a complex number is by specifying in this form. If we write it as 2i or 1i, this represents a complex number. So if you check the imaginary literals, alright, imaginary literals, the I must be present with one of the decimals or integer or floating float literals. So you can write 1.1 I, or if you are representing a float literal, which can be or integer literal, it can be represented with binary digits as well. So this is basically 2I. If you evaluate it, then it should show as 2I. As you can see, it is 02 plus 2I, which is a complex 128 bit complex number. The first real part showing the complex number, the real part showing the complex, the real float 32 represented by float 64, and the imaginary part represented by float 64 as well. So in total it's a complex 128 representation. So that's how we can represent complex numbers. Or if you want to add the real part as well, so we can write it like this. So here, this is the real part, and this is the imaginary part. Okay. Since we are using printf statement, we should be using /n. So if we run this once again, so it properly shows that real part is 3 and imaginary part is 2, and as a whole, and you can see that the real part is float 64 and the imaginary part is float 64 as well. In total, 128 bits are used to represent a complex number, along with for both the including both the imaginary and the real parts. Now let us go to string. Sorry, I forgot about the booleans. So if we want to check for booleans, then there are basically two types of boolean values. That's one is true and false. These are actually constants, which these are actually global constants. So if you run this, you will see that it shows us the boolean. So this true, which is a boolean. But this true is actually, you can override it with any other value, because that's just a constant in the global space, and if you override it and write it like this, but see, Visual Studio actually shows it. So you can see that you can override this value true, and you can also override any of the data types which I previously showed you. So this even bool can be bool as a data type can be overwritten and can be represented. So as you can see here, here your bool was bool value was false. Now if you run it again, bool value is true now. It is very much aligned with the documentation. If you go by the documentation of the identifiers, then as you can see here, you can use you cannot use any of these keywords as identifiers, but but there are some pre-declared identifiers which are the data types that you use. These are actually predefined identifiers, so you can override these identifiers in your function. Even true, false, iota, and nil value functions, these are the universe block functions. These are in Golang, the global scope is called as universe block. So any identifiers represented in universe block can be overridden by any of the local block. So you can override all those values. Now, if we go to strings, string is a data type, so we can represent a string using this double quotations and writing the string within those double quotations, writing the actual value within that, and it will give us the output as the proper string. So you can also represent some of the Unicode values. Let's say you want to represent a Unicode value which is let's go to the Unicode table and check some of the Unicode values that are a bit complicated in nature. I try to represent using strings. So this actually by default uses UTF-8 notation, and if you want to use any extra wide character or wide character Unicode code points, then there is a way to represent that. I'll give you the description how to do that. But let's represent. Let's say I want to represent this value. So this is represented using the Unicode point or 0152. So how you can represent this value is that let's copy the actual glyph and remove this. So this as can be seen, we can represent this using a Unicode point 0152. So if you write like this, then that also represents this particular value. If you can see, this gives us a proper output. And this can also be splitted. This 0152 can be splitted to by two hexadecimal representation, which I just need to check. So 338. So 338 is in hexadecimal. If we go for hexadecimal, what will be the hexadecimal value of it? Not sure where it is represented here. Unicode in hexadecimal. Go for this 0152 can be so if we go for this value, see in hexadecimal notation, this is represented by this number. So if we go for another string with using hexadecimal notation, then we can represent it using like this. If we separate it, then it gives a very different number, which might not be present in the Unicode point. But if we write it without separation, then it very much gives a proper output, proper glyph. So this is how you can represent hexadecimal notations using Unicode wide character Unicode points using this notation. And if we go for much more wider characters like Chinese or any other wide characters, like let's say Odia. So if we go for this is not bigger enough. If we go for Chinese, the Chinese letters have much bigger representation using more than 8 bits. Basically, there are 16 bits. They're represented using 16 bits. So if we go to Chinese notation, how do I search for mathematical musical symbols? Okay, so this, as you can see, this is a wide character. You cannot represent this number. If you want to represent this, let's not say this. If we go for music, this one, this musical symbol, clef symbol. So to represent the clef symbol, so what was the clef symbol? Okay, musical symbols. If we go for this music clef symbol, which is represented by a bigger number. So if we try to represent using this small Unicode, this only takes 4 digits. So you need to have a higher value. So you need this kind of representation to convert it. And if we go for the hexadecimal notation, so this can be written likewise. So as you can see here, it takes 4 words. There is 4 bytes. This is 1, 2, 3, and 4 bytes. So if we run it and try to check the values, then definitely the output screen does not support this glyph, but it does represent that value. If we go for any emojis, let's say heart emoji. Heart emoji is not bigger. We go for any bigger emojis. There will be a family emoji that we can check, because that is a bigger emoji. We can just search for family emoji. Yeah. So this is a bigger emoji, and if we want to represent this, then we need to write this for hexadecimal values. So it takes 4 bytes in the 4 bytes in the memory, and this is the emoji that should be printed. But again, the output screen does not support that. If we use any this is my terminal, then let's see what it prints. So yeah, so now you can see here the emoji is printed properly, and if we check for the older value of the see, as you can see, the music symbol is properly it is chef symbol is properly printed. Okay. Clef, that is the clef symbol. Okay. Now, if we check the these are the various ways you can represent strings. This basically converts to this basically is bytes. And this can be represented. So if we go for this, yeah, so this is a rune type. Rune is this is the rune type, which is basically alias for int32, and this can be converted to string. And it represents a single character. Okay, now this is rune type, and then the if you want to export any of the values from here, then you need to represent the first character must be capitalized. So with capital first character, this will be a public value that can be imported by any other Go modules. So that's how you represent various data types. Now there are various ways. I have been using const and var to declare variables, but you can also declare variables like so, which in this case you do not need to represent. There is no way you can write a data type, but if you assign a value, it will automatically take the it will automatically see the type of the value. It will automatically check the type of value. You can write it as like points. So this is how you can represent uh, you can write variable. There are various ways you can write variables, like using blocks. If you want to write, this is called a variable block. So if you want to write like related variables, then you can write it likewise. So and you can even write it likewise as well. So you can write it likewise as well. So there are various ways, and you can, of course, you can use var here. Sorry, you need to use if you use constant, then you do not need to write the use the variables. But if you use var, then you must use the variable in the program. So if we, as you can see here, okay. Name and age. Name 2, there's 2. So the first one is var const, so we do not, the first one does not need to be written, but the second one that has to be written. If we write it like this, without const, if we directly write it without any keywords, this is you cannot reassign the values like this, and but you can so you can write it like this as well. So this will also print, so you can write variables, assign variables in various ways. If we write if we want to write enum, so you could write it like so. So this basically represents enum. So iota is another predefined value, as you can see from the predefined identifier, pre-declared identifier, constants. It's a constant. So if we go for iota, then it can, this basically represents log levels. So what this is, info, log level info, then debug and error. So these are all constants, and if you want to represent them, then info will be debug. Yeah, one more thing is that if you want this, you need, if the first character is capitalized, then this will be exported, and definitely we want to export a constant. So if you run this, and as you can see here, it automatically increments this automatically increments the values. The first one is a blank value, so we do not. This is actually empty. It is only write only variable, and this does not do anything. So after that, iota increased by 1. So if you want to represent power, let's say you want this to be this will basically square. The first one will iota starts with 0, and then the first one will be 0, and then the second one iota increases by 1, and the pattern iota pattern will be 1 and 2 will be 2. So if we go for this 2, so this represents 2, so this will represent 4, because iota value here, iota value will be 1, iota will be 2, and iota will be 3 here. So if we go by this, 2 square is 4, and 2 cube is 8. So let's see if this properly is represented by like this. Okay, 3 to the power 3. Okay, this is multiplication. 3 multiplied by 2 is actually 8. So this is 3 multiplied by 2 is actually 6. So this is represented by that. And if you want to go by this power, then we need to import a math package. So if you want to, for iota, if we want iota square, if you want to square it, and then this will represent 2, or if this will represent 1, then this will represent 2 square will be 4, and then 3 square will be 9. So if we see, then as you can see, the values are likewise. So this is iota. This is how you represent using iota. Okay. This using this iota, you can represent various enums. Now let us go into arrays and slices. So if we go for arrays can be represent origin. Let's just comment out everything. Yeah, and yes, you can write multi-line comments likewise. So we will just comment it out and keep it below the main function. We can use it later. We don't need it right now. Now, if we want to write a array, let's say we want to go for an integer array. So we can write an integer array likewise. So this will represent an integer array. Okay, this is right. So this will represent an integer array. And if we go by this again from okay, some of the values are not used. Okay, sorry, you need to write this. So this is how you represent an array. These arrays are fixed. So if you want to, so let's say this is nums. I'll just rename that nums, and then this is names. So if we want nums2, so if we want to, if we write it like this, and which let's then if we modify the first value to 9 from of norms2 and modify the first the last value to 8 in nums1. So let's just write it as nums1. Then let's see how does it change. As you can see, nums1 is initialized to 1, 2, 3, and the nums2 nums2 and nums2. Okay, let's reprint that. So nums1 is represented as 1, 2, 3, while the nums2 is 1, 2, 3. Then we change the nums1's last value to 8, and as you can see here, the nums1 last value is 8, and the nums2's first value to 9, as you can see here, and we printed that. So as you can see, it did not print, unlike any other language array in any other languages. These are actually arrays are copied. These are arrays are primitives, and they are copied. So so if you want to only if you want to take a slice of the array, you want a slice of the array, then you need to, if you want a slice of the array, which if you change one of the parameters of the array, then it should change the other values as well. Okay. I'll get to that later. So slice is represented by dot dot dot, and if we, I'll get to this later. So if you want to use a slice, so we can write dot 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 to create a slice. So if we copy a slice, let's say this is nums1, and we check nums2 as nums1, and we want to change nums1 last value as to 8 and nums2's first value to 9, and then again print both of the values. Then you will be able to notice that using a slice actually also copies the value. Slice copied the value. So if we want to, if we go by the definition of slices, arrays and slice, let us see types, numeric types, string, array types, slice types, or slice. Okay, I need to study this one. An array is a numbered sequence of elements of a single type called the element type. Okay, I'll check. We will be checking that. I'll just read it through. Until then, let's pause now.